Okay, so the midterm is almost upon us. Today's all about review for that, and hopefully you had a chance to look at the practice one and its solution. I mean, I'll be going through that. Today's a day for any questions on that. Okay, now how this will work. Keep in mind, this is a mixed undergraduate graduate course, so the expectations are a little different. So for the lightning round portion, for undergraduate for 461, you need to answer 8 questions, any 8, 7 points each, and then your graduate students, you have to answer the 12 questions, they'll be 5 points each. Then for regular problems, there'll be 5 problems in total. Grad students must work all of them, so 8 points each, and then undergraduates can pick 4 out of 5. Let's see, actually, oh yeah, you're real undergrads. Okay. So it adds up to 100 points either way. Okay. Now, I'm not going, because I've been burned on this before, I'm not offering bonus for excess questions. It inflates the scores too much. It gets out of hand.
Did you do that last time?
I did do it last time to a point.
So
Even though I capped it, it's still just like, yeah, it's just either thing.
Now, if you do mess up on one of the problems, like you don't have to, like.
What I will do is, if you work all 5 regular problems,
Yes.
then I will count your best 4.
Okay.
Yeah. So by all means work them, but so it will help, but it's no point. Because also any bonus kind of skews in favor of undergraduates. Okay. Now, what sorts of things should you know how to do? Certainly for the regular problems. Okay, so carrying out, there was an exploration on it. The Gauss elimination with partial or complete pivoting, obtaining the LU decomposition. Really, PA equals LU. So LU decomposition of pivoting taken into account. Also carrying out forward and back substitution. So carrying out on paper, like the whole process of solving A is equals B. And I make a comment here, don't do these problems the NAC 326 way. That's really reference to pivoting. So if a problem calls for partial pivoting, then next to this we carry out. So not just only changing rows if you avoid a divide by 0 situation. And keep in mind what the problem is saying. Okay, so looks like Taylor is about to join us. Well, I've already joined in, but pay attention to the wording of a problem. This is actually something we're commenting on in general when it comes to explorations, concept check questions, support questions on this midterm. There have been a number of instances of people not actually paying attention to what the question is asking for. If a problem specifies a particular method, I'm asking that for a reason. So, like if it says forward and back substitution, then I want to see those processes carried out. Or whatever pivoting schemes ask for. Now, if I don't specify, then okay, that means I don't care. But there are cases where I do care. Okay. All right. So for LU decomposition, we're going to be performing row operations. So as part of our process, we're going to be computing multipliers, and there's a formula for it. And the multiplier is always the entry you actually want to eliminate in like row I, column J, and it's divided by the diagonal entry in the same column. So show that process. If this is not a severe time pressure test, you have several hours in which to do it. So take time to work out the steps. Scan to me however many pages you need to write it all down. Once you have a multiplier, that gets stored in L. And if you do pivoting, then what that means is if you're storing your L as you go, like you're writing out what your L is along the way, if you all of a sudden like you got to column 3, like you need to interchange rows, interchange the multipliers in those rows to make sure that the L is correct. What you could always do is like once you have L, U, and P, if the pivoting was needed, actually check. Does P times A equals L times U? You can check your answer. I'm fine if you're using MATLAB to check your answer. But show me your dang work. So I guess if I ask for what is the LU decomposition of partial pivoting for such and such matrix, and I see a whole bunch of decimals, I'm gonna be a little suspicious. Especially if there's no work involved, no work shown. Okay. Yeah, so here's an example of what I mean about pivoting. So you eliminate the entries in column 1. So then you've written down all these multipliers for column 1, like M21, M31, that go into your L. But then you go to column 2, and let's suppose that in column 2, because of partial pivoting, you feel the need to interchange rows 2 and 3. Then those multipliers in rows 2 and 3, that you already computed from column 1, you have to swap them. So a row interchange doesn't just interchange the rows of the rest of the matrix you're working on, but also multipliers in those rows that you've already computed. All right, so I think I've emphasized that potential gotcha enough. Okay. As far as pivoting is concerned, okay, if it's a partial pivoting, go to each column. On column J, you look in the portion of the column from the diagonal on down. If it's complete pivoting, if you're working in column J, you have that whole submatrix, rows and columns, J through N. You find the largest entry in that submatrix, and then you swap rows or columns as needed to put that largest entry, an absolute value, in the JJ position. Making clear what row operations you're performing. The more easily you can follow what you're doing, the easier it is to give partial credit in case something goes wrong. This actually happened to me in my first numerical analysis course in 1988, when I was, now this is an in-class test, I performed the LU decomposition with Gaussian elimination of partial pivoting and then do forward-back substitution. And the professor set it up so that the answer would work out very nicely. The X turned out to be 101, and I did not get that. And I found out right after the test I didn't get it. And so I was freaking out, like, oh my God, I'm gonna lose points. How many points am I gonna lose? But because I'd written out everything, it turned out I'd done most of it right up to a point, and then they saw I was being well in mistakes, so I lost 2 points. So I was freaking out about that. So the more you show me about what you know, the better off you'll be. Okay. Questions so far about what's expected when it comes to Gaussian elimination, partial pivoting, and all that stuff. All right. Okay, banded matrices. How does LU behave when it comes to banded matrix? avoiding pivoting in that case, so as not to incur fill in. But keep in mind, what is the lower bandwidth of L, and what is the upper bandwidth of U? This came up in a homework question. And what's bad about pivoting? Why do we prefer not to do it in the banded case? Just a few things to keep in mind. Yeah, I'm not asking you now. Yeah, these are things that can get asked, especially like in the lightning round question. Okay, yeah, Cholesky factorization, that's something you should be able to do in following the procedure I outlined in class. Given a matrix, what is the Cholesky factor G? And then as for solving a system, you use the Cholesky factorization, and then you do forward substitution and back substitution with G and then G transpose. Go through columns from left to right to compute a Cholesky factor. Within each column, you start at the diagonal entry, you go to the bottom. Oh, I guess I've given this away. You have the numbers to work out nicely, so but try to make it happen when possible. But at least with Cholesky, it is possible, or easy to make happen. Okay, condition number. So the condition number is norm of A times norm of A inverse. Now, using simple norms. Now, most of the matrix norms are fairly straightforward to compute. The one norm is the maximum column sum. J norm is the maximum row sum. Absolute value, don't forget the absolute value. Frobenius norm is you take the square root of some squares of all the entries in the matrix. Now, as far as computing the inverse, keep in mind this formula. This is the formula for the inverse of a 2 by 2 matrix. So with that, you have all. So in this bullet point here, you have all the information you need to compute the condition number of a 2 by 2 matrix in any one of these norms. Okay, so these are the things that you need to be able to do. So any questions about that before I start looking for the
Is there going to be any question for which we need to write codes?
Sorry, what?
Any MATLAB question?
Oh, there are no MATLAB questions on this midterm. Kind of hard to do those. Maybe we'll take some of the pressure off. Okay. Well, there's many questions, problems here, so I'll just go for them all. And when have questions as needed. So as an example, a Gaussian summation of partial pivoting, forward substitution, back substitution, solve AX equals B with this given A and B. So you start by looking at the first column. We have the entries 1, 2, and 4. You want the largest entry to be in the diagonal position, but the largest entry is down here in row 3. So you have to swap rows 1 and 3 first. Okay, so now we're here. Then, to eliminate this entry, you take the entry you're eliminating, which is 2, divided by the diagonal entry, so 4. So your multiplier is 1/2. And then similarly for the third row, you're eliminating 1, divided by the diagonal entry of 4. So your multiplier for this entry is 1/4. So as you perform those 2 row operations, then you're here. So M1 is a product of elementary row matrices that eliminates the entries in the first column. So now we're here. And once again, you want to make sure that you're looking at column 2 from a diagonal on down. And you want to make sure the largest entry is in the 2-2 position. In this case, it is. So there's no need to do any further pivoting here. So then you take the entry you want to eliminate, divided by the diagonal entry above it, and you get the multiplier of -1/2. Then you perform that row operation, and now your matrix is upper triangular. So this right here is your U from your LU decomposition. And then for L, this is your L. Now, one thing I want to point out about the L is because here's our P, the only swap that happened was swapping rows 1 and 3. So that is reflected in this permutation matrix here. But if I go back to what row operations were performed, so for this entry we use 1/2 as a multiplier, the entry below it we use 1/4 as a multiplier. But now, okay, that's already taken into account because the swap happened first. So yeah, this is the correct L. Whereas if it had turned out that I needed to do a row swap in column 2, I would have had to have interchanged these two multipliers, 1/2 and 1/4. But because the rows were swapped before these row operations happened, they're in the correct position as they. So something to keep in mind. This didn't come up in this example.
I don't understand about -1/2.
The multiplier needed to eliminate this entry. So that's computed here.
Where you take 5/2 times -1/2 and add it?
Okay, yeah, so you take your diagonal entry, multiply by the multiplier, and then subtract it. That's the zero out that entry.
So.
Okay.
I see.
Okay.
I have a question.
Yeah.
So the P takes this form because of row swap. So
yeah.
Whenever we swap a row or column, we have to do it for everything, like P, L, and U for all of them.
Okay.
The row swap.
Yeah.
So P is 001. That was actually the third row, right?
So P is what happens when you start with identity, and whatever row swaps you had to perform, you apply to identity. Yeah.
Question. So it has to do with completeness.
Uh-huh.
Now, if I'm exchanging, so later I would have to. It's a possibility where I'll have to exchange rows and columns, right?
Yeah.
At the same time.
Right. So then in that case, you're
both sides. I
Yeah.
would have to multiply, like have the same matrix, like the same permutation matrix, but multiply it on both sides.
not the same.
Oh yeah, because.
Yeah, so in other words, A will be multiplied by a row permutation matrix on the left and
Yeah.
column permutation
On the
matrix.
right. Yeah, that makes sense. I also. Why don't have the P is this? Wait,
Oh,
I know we switched the first and the third column.
We swapped the first and the third rows.
Or rows, yeah.
Yeah, and that was the only interchange we made. So, and then, like the previous question, you get P by applying whatever row swaps happen to identity.
Mm-hmm.
Yeah.
What would it look like if it were we switched column?
Then there'd be two permutation matrices.
Okay. Okay, so they're not going to be combined.
But that may not come up. Okay, any other question about the elimination process?
I mean, for the regular Gaussian elimination.
Yeah.
Last time I asked, and you said for the lower triangular matrix, we negate the multipliers.
Hold on. In in the elementary row matrices that perform row operations, you do negate the multipliers. But then to get L, those matrices get inverted, which takes away the negation.
What would it look like? I think I'm getting caught up on it, but I don't think about it. What would it look like if it were you interchange row 1 and row 2?
Oh, okay. So interchange just row 1 and row 2. I would have 0, 1, 0 up here,
0, 1, 0.
and then 1, 0, 0 here in the second row. And then if the third row is not involved, it has 0, 0, 1. So yeah, I'd be swapping just rows 1 and 2 of identity in that case. Oh, hot topic. Anything further? Okay. For forward substitution, so you're solving a system with this unit lower triangular matrix. But your right-hand side is your original B, 1, 4, minus 1, with the row interchange applied to it, which is equivalent to multiplying by P. So P swaps the first and third rows. The original B is 1, 4, minus 1, but the first and third elements switch. So now you're solving Ly equals this vector of a minus 1, 4, 1. So we write out what all the equations of the system are from L and then PB. You have this system and it's forward substitution. So you can solve from the top down. So y1 is just given away. And then you substitute to get y2, then substitute y1 and y2 down here to get y3. And this is what you end up with. In case you want to try this at home and check. And then your upper triangular system for back substitution, you take the y that you got from forward substitution, put that as the right-hand side, and then now you're going to solve this equation for x3, substitute that up here, solve for x2, and then substitute that x2 and x3 up here to solve for x1. And it looks like the numbers, 1, 0, minus 1. Well, it's a flashback to 35 years ago. That was 1, 0, 1 in that case. Right. And then you're done. That's your x. So, so show me that Gauss elimination with whatever pivoting is asked for, forward substitution, back substitution. So that way I can see, like, okay, how, in case you do not get the correct final answer, where was the mistake made? Questions on this one? Okay, next one. Here, you're not asked to solve Ax equals B. There's no B here. Just carry out Gauss elimination with complete pivoting on this matrix. What happens is, for the original A, before you work in the first column, you want to find the largest entry in the whole matrix, an absolute value, and perform row and column interchanges to put it in the 1, 1 position. The largest entry is this 9 right here. So you have to swap, there's 2 swaps. First, you swap rows 1 and 3. That at least puts the 9 in the first row. And then you swap columns 1 and 3. And that will put the 9 right here. So this is what you get after performing both of those swaps. For the record, when you have to do like both a row and a column swap, it doesn't matter in what order you perform that. Matrix multiplication is not commutative, but it is associative. We can do either one first, and the result will be the same. So now that largest entry is in the 1-1 position. Then you do Gauss elimination. So we have -6 divided by 9 for the multiplier for this row, so it's -2/3. And then you have 3 over 9, gives you a multiplier of 1/3 for the third row. So then you perform those two row operations, and now you have this matrix. Now you move to the second column, and then you're going to check rows and columns 2 and 3. So this 2 by 2 submatrix down here, which is the largest entry, and you want to make sure that's in the 2-2 position. Thankfully, the largest entry is already in the 2-2 position. It's right here, 31/3. So there's no need for any row or column interchanges in that case. So then you just need the one multiplier, so -14/3 divided by 31/3, and you carry out that row operation, and now you have your upper triangular matrix. Questions about complete pivoting? Okay, nice. The other Gauss elimination one, but with partial pivoting, but now the matrix is banded. Don't forget the questions that are asked. Okay, so you're going to have compute PA equals LU, so I need to see as part of your final answer, L, U, P. Now, when you do Gauss elimination on a banded matrix, there's expectations about going from lower bandwidth of L to the upper bandwidth of U. And you're asked, does that match? And if not, why? So what happens is you're trying to get this matrix, and you have 0 in 1-1 position. That certainly won't do. So what you need to do is perform a row swap. You're going to swap rows 1 and 2. We're only doing partial pivoting here, not complete pivoting. So now we have the largest entry in column 1 is in the diagonal position. And now there's no non-zero entries below it, so we're actually done with column 1 now. Then you move to column 2. Okay, no pivoting needed because we have these entries 1 and -1, so the largest entry is already in the diagonal position. We do have one row operation to perform with a multiplier of -1. So then you carry out that row operation. And so after working on column 2, we're here. Then you go to column 3 and you look at column 3 from the diagonal to the bottom, and we need to do another row interchange. So we swap rows 3 and 4, and now we're done because the matrix is number triangular. So what ended up happening is we have these. Here's your P from swapping rows 1 and 2 at the beginning, and then we're swapping rows 3 and 4 later. L is almost identity. There was only one elimination operation performed, and that was back here. We needed to use this row, second row 2, to eliminate an entry in row 3. Now, so it's kind of strange that we eliminated an entry in row 3, but the multiplier is sitting in row 4. Reason why is, after we worked on column 2, rows 3 and 4 got interchanged. And so these rows 3 and 4 of L also had to be interchanged. That moved the multiplier of -1 down here. So there's a comment about that. So beware. This is why it's a good idea if you compute a decomposition. Actually, multiply the matrices out. Make sure you get what you're supposed to get. And then your U is just the matrix you wound up with after Gauss elimination was completed. So now the thing is, normally with a banded matrix, the lower bandwidth of L should equal the lower bandwidth of A, and the upper bandwidth of U should equal the upper bandwidth of A. But that didn't happen here. I mean, A, the original A, had an upper and lower bandwidth of 1. But L and U both have like a bandwidth, like lower and upper bandwidth respectively of 2. And the reason for that is the pivoting. So saying that the statement that, okay, the lower bandwidth of L equals the lower bandwidth of A, and the upper bandwidth of U equals the upper bandwidth of A, is only valid if you're not pivoting. So once you do any pivoting at all, any expectations about the lower bandwidth of L or the upper bandwidth of U are out the window. Anything goes in that case. So questions about Gauss elimination, partial pivoting, or banded case?
Partial pivoting only within the column,
Rows.
or in the rows.
Yeah, you only swap rows. Yeah, so you're examining a portion of a column, and only that column.
Okay.
I think I only have a couple more of these to go through. Okay, Cholesky factorization. So really, the answer we're looking for is G. What is the Cholesky factor, the lower triangular factor? This symmetric positive definite matrix. So what you do is you set A equal to G times G transpose, and what you do is you work out this product, this matrix product, and equate the results to the entries of A. And that can help you solve for all of the entries of G. And I did an example like this in class. So for example, A11 is equal to, so you take the first row here, first column here, and this is G11 squared. So G11 is just whatever A11. Always take the positive square root. The Cholesky factor has to have positive diagonal entries. And then you go to the 2-1 entry. So you take the second row, dot product of the first column. So it's G21, G11, and G11 is known already. So then you can take this equation and rearrange it to get G21, and then you just keep going. So you go through all the entries in the first column, and that's laid out down here. And then for the second column, you start with diagonal entry. So A22 by the matrix product is G21 squared plus G22 squared. But G21 was computed earlier. So then you take this equation and you rearrange it to solve for G22. Again, take the positive square root. And this process just continues, that as you visit each entry in the lower triangle, including the diagonal, of A, and you get a formula for that entry in terms of the entries of G, matrix product, you'll always have a situation where all of the entries of G that are involved are known, except one. And then you just rearrange and solve for that entry. And then once you get all the way to the last column, you end up with a square root for the last diagonal entry. Then you have your G, and you take time to check. Does G times G transpose really equal A? So questions about Cholesky? Yes, you could put the matrix in the MATLAB and have it you call Chol and get a Cholesky factor, but you better show your work. Finally, okay, all right, condition number, in the infinity norm of this matrix. Now the condition number is equal to the norm of A times norm of A inverse. So we need the inverse. Now, I did give a formula for the inverse earlier, or you can just take this equation, A times A inverse equals identity, And then you have formulas for all the entries of the inverse, so you could do it that way too. And these are the entries that you end up with, so not so nice fractions. Okay, so then we use a formula from a condition number in the infinity norm. So it's equal to the infinity norm of A times the infinity norm of A inverse, which I'm calling B here. And here are those matrices. Here's A and here's the inverse. So what you do is you take the maximum row sum. So here we take a row sum here, 1001. Here for row sum is only 3. Do not forget to take absolute value. So in this case, the maximum row sum is 1001. So this 1001 is the infinity norm of A. And then you go to the inverse. And here we take the absolute value of all the entries and add them up in the first row, and we get 501 over 499. And then for second row, you just get 2 over 998. So the first row sum is the larger. So that's why the infinity norm of the inverse is right here, 501 divided by 499. One thing I want to point out is with determinants, the determinant of A inverse is always 1 over determinant of A. We don't have that kind of relationship when it comes to norms. The norm of A turned out to be 1001. The norm of A inverse turned out to be a number that's only slightly greater than 1. So you don't have that like reciprocal relationship. So then you just multiply that out, and this is to a few decimal places the approximate infinity norm condition number. Okay. Yeah. So in the copious amounts of time we have remaining, do you have any questions about this? I've been trying to stay caught up on grading. I've graded all quizzes that have come to me so far. I mean, those high priority. But I'll make sure to grade everything comes in. So I would recommend, if you haven't completed the concept check quizzes, I think there are only 3 of them for this chapter. You should do that because that can be helpful for your midterm preparation. For the regular homework and the explorations, test your code. Sometimes I see someone's code, and I can tell just by looking that they haven't run that code. I can tell, like, oh, this is going to crash, or otherwise be incorrect. So be sure to take time to do that. If you're not sure what's a good way to test your code for a particular problem, I've mentioned that in certain cases, but if you're not sure, you can always ask me about that. Please do not commit code that hasn't been run. Save me some time and save yourself some points. Well, yes, that's it. Okay, so we do not meet on Monday. So around 11 a.m., class time on Monday is when. So look in Canvas, and it'll be posted there. So eventually posted there. What I will do, I'll post the document as a PDF like I normally do, but I'll also post a LaTeX file. So if you'd like to give your answers in LaTeX, you can do that. You should write something. Wow, it's a short class.